Excellent. Good morning. This is George Laird, and it is 8:30 Pacific Coast time, and I'm starting the seminar. And I also have my staff engineer, Adrian Jensen, online. Adrian, say hello.
Hi, everybody. Good morning.
Good morning. You guys can't talk. We get a. If you turn on these webinars, if you allow everyone to talk, you just get this gigantic ruckus going on. But what you guys can do is that you can send in questions. On your panel, you can write up questions, and while I'm talking, Adrian can sort through them, and he'll answer the ones he can, and he'll organize them up, and I'll answer them either during the seminar or at the very end, or email later on if we run out of time, because there's lots of material to cover. This is pretty dry stuff. I hope you guys don't fall asleep. It took me a lot of research to put these notes together, and I was even putting things together this morning. It's amazing how little I knew about these connections. And so here's what the general outline where I'm going to try to talk about. Why is this worthwhile to have in your tool chest? Why should you even want to listen to this? Well, you guys are far ahead of the curve just to even be here. Just to even take time out of your schedule to listen to this stuff. You're far ahead of the curve on learning, on analysis stuff. So what we're going to go through is the basics about how RBE elements are formulated, and I want to talk also about using spring elements, specifically the CBUSH, and at the very end some FEMAP tips and tricks. All these notes are going to be available after the seminar and along with the models, except these two models. These two models are proprietary, but everything else will be in a zipped up package. It'll be on the web next week. You can download it, and I'll have the seminar live, this actual video, along with all the models and these notes. Why should we even bother getting into this? Any real engineering system model will be using RBE2s. Of some type, RBE2s or RBE3s or multipoint constraint equations. They're everywhere. For example, on this large model of a research satellite, we're using a rigid link to tie into a large mass sitting on top. And then the bolted connections, we're using an RBE2 again to spread out the bolt load into the plate elements and through a beam connection. And at the very bottom, we're transferring the PSD load at a single point to another RBE2 into the frame. And this is a model of an engine transmission. It's for a 3,000 horsepower, 12-cylinder diesel motor. And going inside that, RBE3s were used to distribute bearing loads into the bearing cuffs. Of course, RBE2s were used to connect up all the beam elements and make all the bolted connections. Very, very complex model. Yeah, page 2. Okay, I'm just going to use page down. Page 3. Nastran, when they introduce it into the element library reference, I don't find this very helpful. They throw all these terminology at you: rigid element and MPC and entries. And the only ones I really recognize are RBE2 and RBE3. The R-rod, R-bar, all are rigid triangular plate, I've never used. RS-spline, never used. RS-con. Multipoint constraint, just vaguely. What I want to try to introduce the concept that all of these connection technologies are all just multi-point constraints, MPCs. They're just different formulations. Think of them sort of like hard-coded up. They come with their own coefficients. And in the preprocessor, where you're creating your rigid body elements, they're just putting in the coefficients for you. But if you're very clever mathematically, you could handwrite them all as multi-point constraints. So I came out of an ANSYS background, and this concept of single point, multi-point, what the heck is that? It was always constraints. In Nastran, there is a distinct logic to it, and there's a good reason why they they formulate like this. Single point are just your standard constraints. You take a node, you constrain it. A multi-point constraint, this is where it gets much more interesting. They're still constraints. We're not making an element. We're not adding to the stiffness matrix. What we're doing is we're saying this node over here can move like all these other nodes, or we want this node to drive these other nodes. Or you could reverse it and say we want this bunch of nodes over here to drive one node. So you can flip them around and move them back around, but at the end of the day, it's all based on constraints. It's all based on making constraint relationships. And the way you make those constraint relationships are called constraint equations. And if you've been working with FEMAP, you've seen constraint equations, and I can say I really never dug into it and said, well, really what the heck is going on in the equation? I just went straight to node. You know, we've seen this, pick a node, and let's apply a single point constraint, SPC. That always seemed to make a lot of sense, and I never really dug into what the heck is an equation. The equations are your multi-point constraints, and I'll talk a little bit about that, how you make them. But this is the foundation for all your rigid body elements, all that other stuff. Okay. People say, how do I dig into this stuff? How do I learn more? The NX Nastran literature is really quite good, and it comes with every FEMAP install. Help, NX Nastran, and I go to the PDF. And it is really, I mean, it's dense reading. It's pretty thick, but it's really useful. It's very, very helpful to understand some of the foundations. Okay. This is new in that when it first came out in 10.2, I sort of complained a little bit about how they move things around for the RBE2, where in prior 10.2 the independent was to the left, and I liked that workflow. I thought, oh yeah, you just pick the independent node and then you go ahead and pick the dependent nodes, and that made good sense. And this came out and it was reversed, and I couldn't quite figure it out. And you go over to the RBE3 and they have this same way. Dependent is on the left, independent is on the right. And what they're saying in mathematical formulation is that your independent node is driving the dependent nodes. So the dependent nodes are the ones are actually being driven. This is why on an RBE2 you can apply a constraint to it, and how this, if you apply it to the independent node, it will drive the dependent nodes. Likewise, in your RBE3, this is where it makes good sense. The RBE3, here's your dependent node that you pick, and here's all your independent nodes or master nodes which are driving the dependent node. Dependent means, of course, it relies upon all the other nodes to do its work. Now I don't expect, it's one of those things, it's taken me a while to get my mind around it. It makes sense once you start sort of working with it. If you get this Adrian, do you follow what I'm trying to say? Does this make sense? I'm trying to introduce this.
I think once we have an image showing kind of the spider of an RB2 or any sort of element, we can compare the master independent versus dependent.
Right. I know, it's just like this is the foundation of where this is all going. And this is one of the little things that can catch you if you're doing nonlinear work. Rigid elements, they stay rigid. They're in the constraint equation. They're updated once. They're not like an element or change. And so if you're doing any sort of nonlinear work with rigid elements, you can maybe get some unexpected results. And it's just something to note. Of course, if you have a zero length element, it doesn't matter because there's no length to update. So the first model. This will make it a little more helpful. You guys won't find it so dry. This is a basic, simply supported beam, and I fixed the ends. So it's completely constrained. It's not going to spin off in space. Both ends are fixed. We put a load out in the middle, and we use a rigid link, an RBE2, to constrain the load. And I want to go in and talk about how you set up the turn-on equation force so you can extract the free body diagram information, and we'll look at the FL6 file too. And this model file, first RBE model uniform. So this is something that you guys afterwards can get a hold of and use. Okay. You also might notice I have different colors set up and different shading, and I'm very, very keen on customizing my graphics view. Modify, edit, element. This is the RBE2. I'm telling it that node 1 is right here in the center. And I'm telling this node here, well, I've been playing with it before, is that I want this node to transmit RZ and TY. I want these to follow. That as this node moves, it's going to move these nodes to TY and the RZ are going to be the dependent. Now why did that die? That's what I get for messing things up. RBE2. It's a long story. What that error message, and I jumped around. Let's go back to where it was. There we go. That error message, and when I do these presentations, I get a little nervous. You're talking to a big crowd of people, and the error message that jumped up, my antivirus program that I'm using, Kaspersky, sometimes will hinder the Nastran file when it's looking around, and it will give a false error message. So that's what that was. And then I just double-clicked on the Nastran file manager, and I got to bring it back to here. Let's lock that. Okay. I've been using dual monitors, and so the Nastran Analysis Manager was off on the other dual monitor. All sorts of little hiccups. Okay. What you're seeing in this model is that you have the old load resultant showing the 100 pounds. And then you have your SBC resultant, and then you also have down below your MPC force resultant. This is sort of your clue saying that all rigid elements, all RBEs, are multi-point force constraints. And this sums to 0 as it should. And all your loads are going to the old load and SBC force. Now, in this setup that I have managed here, to get your MPC force resultants calculated, you have to turn on equation force. So this is the default. In the default mode, let's just go ahead and run it. Because I know these little things are sometimes, it just kills you. You're trying to figure out what the heck is going on, and you think things are broken, and there's not really clear documentation to say you must turn on equation force to get multipoint. So there what I did is I turned off equation, and you get the O load and you get the SPC force, but you do not get the multi-point force constraint calculated. That's empty. And in your free body diagram, there's no multi-point force to calculate. So let's go back to that, turn that back on. Fortunately, I only have to do this once for this seminar. Equation force. So that's going to calculate out your multi-point constraint forces. Nice having this simple model. Runs fast, goes quick. Okay. On the free body diagram, what you're seeing here, in the default, of course, you don't see that. There's none. There's our load, 100 pounds. Free body, let's show it. Let's only look at reaction loads. I hope I'm not going too fast on that. You saw it. Show free body, reaction loads. That's going to be at your constraints. You can get that as a default. Now, let's go back in and let's do multi-point reaction loads. That is your rigid link. So this isn't hard to understand. This can make sense. You go, okay, 100 pounds going down. This little model is real simple. 5 units, 5 units, 5 units. And it's just nice and logical. The sum of forces must equal 0, 50 going down. Here it's 2.5 units, 50 pounds. There's our moment, sum of moments, we're good to go. There's nothing, you know, rigid links give you a nice warm fuzzy. They're pretty direct. Now if we want to play with this, let's turn off the moment. So now we're just going to transfer Ty. This is the independent, and what's happening is this node is driving these two nodes. Boom, 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 boom. And it's nice. I like having the free body diagram on to do these sort of basic mechanics. So now you're at 50 pounds, 5 units, 250. You see how the ins change there? Hey, basic, direct. I think most everybody feels pretty comfortable using RBE2s. It's rigid. Everything connects up pretty clean. Now let's jump off into a little bit more theory. I introduced the concept of multi-point constraints, and I didn't really talk directly to it. Now let's talk right straight to it. And let's sort of make our own little rigid link. And what I'm doing here with the beam is that I'm going to take that same beam and I'm going to define an equation. And the way it's set up is that your first term is your dependent node. Depends upon the movement of the other independent master nodes. So they would say start with an equation like this. Like here is your dependent node, here's your independent, and your first node here, as you defined, is going to be your independent. Excuse me, your dependent, and then the others are the independent. So what I'm saying is that I want this node here in the middle to be dependent upon the movement of these two right here. And I'm saying that to make this work for 1 unit in the center, we have half a unit there and half a unit there. 0.5, 0.5. And if we wanted to modify edit, constraint individual, constraint equation. There's only one. I'll just select all. And that is the constraint equation. Like that. I mean, they're not hard to set up. It's just tricky the first time you do it. And you notice that I've slid the node over to here. Let me go ahead. Edit, move to node. Let me set it back between. I want to set it back to that point in the middle. I'll run it. The point about MPCs, it doesn't care where your dependent node is sitting. It's not spatially dependent. So there's that result there. And if I undo, Control Z, Control Z, Control Z, back to there, let's rerun it. And I have these models saved with results, and it's the same. So I can also show it like that. This is the very powerful concept on multi-point constraints. You can develop constraint relationships however you want to do it, just by using this equation. It's a very, very handy thing to have. There's another thing I want to show. You guys aren't going to get away that easily. We're going to do some math. Okay, web meetings, connections. Where is it? NX Nastran, theoretical manual. There. Static analysis by the displacement method. That is what we're doing. We're assembling stiffness terms, K, and then we're multiplying it by a displacement matrix is equal to the forces on the structure. Our unknowns are the displacements. And for multi-point constraints, they're assembled like this. Here are where the coefficients are supplied by the user, RG, and here are the nodal constraints, UG. So this RG, when we're doing an MPC by hand, by formula, we're directly entering the RG. When we let FEMAP say, give us an RBE2. Well, an RBE2 is mathematically defined by a set of coefficients that's been hardwired and all set up for you. And you just pick the nodes and they'll figure out the right coefficients for you. RBE3 the same way. But when Nastran processes them inside the code, it's converting them to coefficients, RG, in this form. Then, naturally, the way this whole matrix method always works, is that you have your independent and your dependent, your UM. And the dependent degrees of freedom can be removed from the matrix because they're defined by the independents. So this relationship is so mathematically, heck, if you're dependent, you don't need it. That's why it's dependent. You can remove them from the matrix. You can write a formula to define one in the form of the other. And that is what this math is going through. It's saying, okay, we can take the coefficients, we can take displacement, set that equal to 0. We can write up this singular matrix GM in the form of that in the masters. Now we can write these dependent degrees of freedom in the form of this matrix times the independent degrees of freedom. I know this seems maybe way unnecessary, but where this is going to is that the reason why it's such a powerful technology is that if you couldn't use these sort of multi-point constraints to create your spiders and relationships for both heads, if you had to go back and use beam elements, extremely rigid small beam elements, you're creating terms in the stiffness matrix, and these terms would be very large, and it could cause the matrix to be very, they would call it ill-conditioned. And when it starts getting ill-conditioned, then bad things happen. It can affect other results. You can get incorrect results. It's something they addressed many years ago, and they said, this is much better to do it via constraints, and this technology is still in use today, and it's really the way to go. But it's all focused on constraints. And so what this is showing here is that, okay, here's your stiffness matrix, here's your displacement, here's your forces. So we're separating it between independent, dependent, and at the end of the day, we're done, and we're back to our standard form of your stiffness matrix times your displacements is equal to your forces. And that is the mathematical foundation of the multi-point constraint and the rigid links. Okay, I'm going to close this out. Enough on math. We'll go back to the pretty pictures. Okay, RBE3s. I'm going to start off comparing them RBE2s, and then we'll show how the mathematical formulation works for RBE3s. And this model is start RBE3 with moment load conditions. There. Okay, close that out. Our simple beam model, it's all 6 degrees of freedom are fixed at the ends. Model's 15 units long in all. Each section is 5 units. Then I put a straight moment load onto it, 1,000. And in the RBE2, it's completely rigid. So what you're doing on a completely rigid element is it's defining the motions at these 2 points. And let's look at that, what I've defined. I've said that I want that to move in the y direction and the z direction. So what it's going to do is it's going to tie these nodes, it's going to make this move as a rigid bar. And if you look at the displacements, the T2 translation is minus 0.0149. And over here, the T2 is minus 0.019. So they're not quite tied together, but they're moving via this moment. That is, what am I looking at? Oh, I said, I was looking at going, this is not quite right because I'm not looking at quite the right output set. And I know everyone out there, they've done that too. When you have multiple output sets, it was set to the force because I'm doing 2 loads. Let's jump to my notes. I'm doing 2 loads here. I do a moment load and a force load. So that's why it wasn't making, I was going, that's not right. Let's go back and look at the displacements. So this is 0.0158. And this is minus 0.0158. So what's happening on the RBE2 is it's constrained in the y and the z. So this is down minus 0.158 and this is up 0.0158. It's rigid. Rigid links transfer stiffness. And since we've tied the y degree of freedom and the RZ degree of freedom together, we've said this is an infinitely stiff constraint. It's being applied via constraints, so it's going to be infinitely stiff. And we're saying this bar here, we're giving 1,000 units of torque. So this bar is just twisting. I mean, it's just twisting. So of course, it's going to apply, it's got to keep this face flat to this face because we're constraining the RZ moment, and we're constraining the Z. So it's perfectly rigid element that's moving it. And that is why, if you just look at the RBE2 moment calculation, you go, these are some weird forces and moments, because here's the moments, it's 270.88, and here's the force, 91.647, and yeah, it sums to 1,000, doing the math, but how in the heck do you get those numbers? I mean, you can't do it by just a standard sum of forces, sum of moments calc. And the reason you can't is because this model here has a rigid link within it. And this rigid link is enforcing to keep in this face flat and this face flat. So that these numbers here are based on this rigid link implementation. And it's just not straight sum of forces, sum of moments. And if you got out your Timoshenko strength of materials and you worked through all the numbers and stuff, you would arrive at this 270.88 because it's rigid. So I know that was rather long, but it's an important point to sort of beat down, that the rigid is you're adding a completely rigid member into the stiffness of the structure, but it's done via constraints, multi-point constraints. The RBE3 doesn't add stiffness. Remember how I was saying that the dependent and the independent concept? Go back, and how in the RBE2 you have your independent with 6 degrees of freedom and deriving your dependent degrees of freedom, and here in the RBE3 your dependent is one node and it's being driven by all these other nodes, all these independent. It's reversed. And this is the stiffness relationship, and this is why in the RBE2 it's transferring the stiffness, and the RBE3 it's just transferring the load, because it's dependent on all these other independent nodes. So let's see how that works. So here our dependent node, which is here in the center, we're trying TY and RZ. And our independent nodes are these two nodes, 2 and 3. You see how they highlight out of the box? And to make this model work, to be stable, this is one of the really sneaky things on RBE3s, is that an RBE3, the independent, you're defining a complete, think of it as a rigid body, a matrix, and it has to be stable in space. It has to cover all 6 degrees of freedom. An RBE2, the independent node, contains 6 degrees of freedom. It's already rigid. And of course, if you lock it down to these ends, it's done. An RBE3, that's not the case. You have to have sufficient degrees of freedom to lock it down. So in this case, watch what happens. I'm going to run this model. I'm going to uncheck the RY for that model, like that. Fatal error. Let's see what it says. Let's go here to FO6. RBE3 element 11 is singular. User action: add more DOFs to the connected points to ensure that they constrain all 6 rigid body modes of the element. And I tell you, I never quite understood what the heck that meant until I started preparing these notes for this thing. And what it means is that if you think of this as a structure, and you could go through the rigid body motions and say, well, we have this pinned at 1, 2, and 3, so that takes care of the translational. Now let's go through the other 3 rotational. Well, around the RY, well, that's addressed by the translation at both ends. Let's look at the RZ. Well, that's addressed by the translational degrees of freedom at both ends. But the RY, the drilling degree of freedom, RY down the axis, is not addressed by the independent degrees of freedom. It has to be done by the dependent. You have to, when they talk about that, they're referring to the independent degrees of freedom to locking those things down. So since the independent nodes are along a straight axis, you know, if this leaves you completely, you're going, what the heck am I talking about and stuff, feel free to talk to me later, because it took me several tries at figuring this out. So if you're straight down the axis like this, then your independent degrees of freedom are collinear. You have to constrain that axis with a degree of freedom. So that is why you have to go in here on your independent nodes, and you have to lock this down. Then when you run it, of course, it doesn't work. Let's see what happened. In file management. Geez, interesting. Let's just run it again. Very odd. My antivirus software today. It's just sort of like, of course, that was a new one. It's never done that before. Now, as you see, of course, it ran just fine. And here's our MVC force, and there's other things. And voila.
So, George, another good point that this slide or this model makes is, as far as organizing your RB2s and RB3s, that the one in the back, the RB2,
yeah,
we're applying the load to the independent node in the center. And for the one in the front, the RB3, it's actually switched. The dependent node is that one in the center.
Right. It's reversed, and that's the concept between RBE2 and RBE3. And here's, I put a little note down at the bottom, said for the RBE3 element, we must include the TX, TZ, and RX DOF on the independent side to prevent rigid body motion. Now remember, all we're transferring here is RZ and TY as in the RB2, but we must include these others on the independent. So, okay. Before I jump too far, I told you guys this is going to be technical. Where do I want to go? On the RBE3, it's in the moment here, of course, it's not going to be dependent upon the location, but you notice how you get the forces of 100, and this is at 250, because it's splitting them up evenly. When you do an RBE3, it's just dividing them up and splitting them. If we look at the forces, we have the even moments, which doesn't, you look at this, you get even moments, and the forces vary, but they don't vary based on, it doesn't, you get 35 over here, 65, and this is based, of course, on the stiffness, so it's going to be based on the stiffness of the member. But the RBE3, when you look at it, you're going, how is it calculating those forces? And that is based on dependent to the independent. And what they're saying numerically is that you have a group, you have a motion of a dependent grid is a weighted average of the motion of a set of independent or master grids. So here are your independent grids, and this is the master grid you want. You want it to behave upon all these other nodes. It's not a rigid element, it's an interpolation element. It does not add stiffness to the structure. So the way it's calculating the forces is that your reference grid or your dependent grid is over here where you're applying forces. Mathematically, it takes the center of gravity of all your independent grids and then it transfers that force and moment to that center of gravity. Just basic math centers that over to that center of gravity. And this are the equations, the way it works out. When we're doing a moment, it moves it to the center of gravity of your two independent nodes, but there's no force to add, so it's just 1,000. Works right out. Quite direct, quite easy. Here, since we have a force, we're moving over to the center. So now what we're doing is the force is the same, but we have a little bonus moment to add in. And then that bonus moment, you just divvy up those forces and moments at the 2 points, and you're done. Very direct, logical. Because you're not adding, since we're not adding stiffness, we can just do sum of forces, sum of moments, free body, done. Nice and simple. Okay. More RBE3s, moment load, force load. Now we're saying we have a RBE2. We're only transmitting rigidity in the y direction. And it's for a moment. And the RBE3 in front, it's not doing anything. It's stable, but the dependent Ty, since we're not transmitting moment, it can't transmit anything to the Ty. There's nothing there. So that's what you, of course, based on that, you get nothing. If we switch it around and go to forces, like that, now we can transmit. And here the RBE2 and the RBE3, it works out the same. Because we're only pushing on the Y. Uses for the RBE3. I think of it as force spreading forces around. Making very sort of when you just want to connect forces from one part to another part of the model. This is an example of where we have a tube with internal pressure on it, and we're connecting it up to a B model, and it works great. Here at the very center you have your dependent node, and here's all your other independent nodes. And your RBE3 makes that perfect connection between the two parts. Let's look at that RBE element. And if we just take a peek, for the RBE3, none of the rotational degrees of freedom are constrained. And they don't need to be constrained because you're dependent, here we're dependent is all 6. The independent, since they're around on a circle, they can constrain all 6 degrees of freedom with the displacement. And that is one of the important things about RBE3s, is that if you over constrain them, the matrix, the actual mathematical procedure can't solve. So here's an example. This shows it nicely set up. I'm pushing up here at the end. I'm constraining here. And you get a very nice load transfer into the structure. And I have the undeformed shape turned on. So I can turn that off. Post processing, undeformed model. Like that. That works great. Now, let's say I go ahead, edit, element. I'll pick these nodes here. I'm going to update it so that they're all checked. This was the last state of the model when I was using it. So these are all checked. Now, let's run it. Results, like that. So now we have a stress of, what is that, 1,214,000. Here's the right answer, 33,000. Here is with the RBE incorrectly set up. And the deformed is 46, when it should be 0.118. Pretty crazy. And the reason that is that when it's forming a matrix inside, and when you over constrain it with your RBE3, it can't figure out what to do. It just basically blows up mathematically internal. It solves, but it's just lost.
Hey, George, can you show the multi-point reaction loads for that garbage output set?
Yeah.
I mean, when you look at those displayed on the model, you might kind of see why the results
are so cooked.
Yeah, not what you want.
Right. Okay. Let's see. This is it. Back over to there. Active. Okay. Let's turn on equation force. Okay. Like that. Want to make sure it's still all set up. So I didn't turn on the multi-point force constraint, the equation calculator. And now, with it turned on, you get the multi-point force constraint that comes up. So now let's go ahead and look in free body display. There you go. Quite bizarre.
Yeah.
I mean, it looks sort of right, but you see the stresses. Modify, edit. Now let's go ahead and correct the element. Voila. Thirteen. Isn't that weird?
You can also see the direction they're pointing in the incorrect configuration is kind of wildly, whereas this one,
God, look at that.
Yeah,
Yeah.
They push on top and they pull on the bottom.
Yeah, I know. Just not even sense. I mean, so this is the concept on the RBE3s is that you have to create a fully constrained body, but you don't want to over-constrain it. Check your work. Check your work. RBE3 usage guidelines do not specify rotational DOF for independent nodes except when necessary to avoid singularity caused by a linear set of master grids. Remember I was saying down the axis, linear set. Using rotational DOF on independent grids can result in implausible results. Yep. Okay. We're 10 minutes left in our hour. We're almost on schedule. I'm going to make this. The CBUSH element, people are using springs. When you go into spring damper, the default is not the CBUSH. And I was talking to the FEMAP development team about why it's not the default. And they said, well, it came later in the Nastran formulation in the sense that it's an element that's later. It came about 10 years ago. But the original formulation was a CELAS, so they felt like since it came later, it shouldn't be it's not set as the default. But they said really it should be in the version coming out 10.3, it's going to be the default. So when you pick spring damper, boom, it's going to go to CBUSH. It is a great spring element. 6 degrees of freedom. It's exact. It's clean. You don't run into numerical problems. The dilemma, the reason why I push on this is that the default CELAS can cause numerical problems. You can get it will actually keep grounding problems in your matrix and suck out energy and could potentially give you completely bogus results. The CBUSH will never do that. It's a very, very clean element. So setting it up, you have to cover 6 degrees of freedom. And so if you're using it on our simple beam model, it works perfectly because 6 degrees of freedom are covered here on the beam. So here, this is my setup. I just want Y. I have it set to the orientation system. Global, Y is vertical, voila, simple, clean, done. You can also have it transfer rotation. Just put a rotation coefficient down. Very direct. This is where it gets it can screw you up a bit. If you attach it to a solid element has 3 degrees of freedom. The CBUSH, if you think of it like a beam element, it makes perfect sense. If you just hang a beam off to a solid element, it's going to swing around, move around, you're screwed. The model's going to be unstable. And no matter how you change these numbers here for stiffness, it's still going to go unstable and blow up. So what I do on that is you just take one end of the beam, of the CBUSH, and I constrain the rotational degrees of freedom. And you're done. It's constrained. You're off to the races. No problem. Tips and tricks. I've talked about this before. File, preferences. It's well hidden. It's been out for a while. Views. My default is PNG animation. Resolution. Check this out. Screen cell by 1. Well, what does that mean? Well, let's copy the picture. I need my PowerPoint. I'll copy that in. Like that. Okay. Now, let's go back to that file preferences. Resolution. Go back to my default of 4. Boom, 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 boom. You notice a little pause there? Now paste. A 1 and a 2 and a 3. A little bit bigger, huh? So what that resolution does is it takes the graphics and it has it draw. I set it to 4. And it allows you to just make absolutely stunning high-res graphics that way. and you can just keep zooming in, and it for very small images it really is great. I mean, you just get so much more detail, where on the 1:1 screen resolution it can look a little grainy. So that was a new feature. Then another thing that I have been doing is, again, under preferences, database, interfaces. In the default FEMAP mode, create references on open, create geometry references. This is the default state. And what FEMAP is doing is that when you bring in references, when you bring in geometry, it makes a record of it here. And it locates it. And if you update that geometry, bring in a new piece of geometry, it logs it into the model file. And let's say you wanted to update or move it in, it will always check. It always creates a link out there. For my models, I bring in a chunk of geometry, and then it's hasta la vista. I'm done with it. I'm always doing other things with it. I don't like to have that tied around, and it clutters up the database, and it always pings me and asks me every time if I want to update it. So this is something I always turn off. File references. And then housekeeping. I like to point all my Nastran files, the FO6, all the OP2, everything to scratch directory. It's just housekeeping. Lastly, I'm going to make it view settings. You can see my settings is quite a bit customized, the way I set things up. And we even have a standard file. Predictive engineering. This is all my API scripts. Standard recommended view settings. It's on our website. And okay to update references. Interesting. I thought I had that turned off. References. Use references. Okay, remove all. Done. Then that won't bug me anymore. This is all in a database. Create, manage, we'll manage, give it a new title, update title. And a lot of you guys know that once it's saved, you can go in and save those view settings, save view to a library, done. And if you had a new view, create view, new view, like that, done. Where is that? It's not that. It's a view, yeah, new window. That's what. Default view, fine. I haven't done this in so long. Nope, default view, default settings. You know what, I'm trying to get it to go back to default. Where do you load the default setting?
Oh, the default FEMAP?
Yeah.
Visibility reset view? No, that'll reset
No.
to your
Default. It's been so long since I've done any of this. So this is for your whole view window, and I just want to set it back to just base level. You know what I mean?
Yeah,
boring ass. Yeah. Blue background. You know, basic view. And I have no idea where I've hidden it. Like that. It's been so many moons, so I know what I'm going to do. Is I'll just load a FEMAP example model. There we go. With the standard background, and there's some results on it, and we can contour it like that. People have seen that before. Now, let's go and load a view. That's a view that we saved. Like that. I'll get the job done. Voila. And if you want to see that view come up every time you do a new window, I am getting, this is where you set it. Startup view from library view number. And that's your library view.
Oh, there you go. So if you enter that to 0 and open a new window, it'll take you back to the FEMAP defaults.
You're right. 0 default, and that's why it wasn't doing that. Good. Learn something new every day. Hey, 9:30. We're done. Page 20 of 20. Adrian, any questions that came up, or did everyone fall asleep at this?
No, it's pretty quiet out there.
Yeah, it's pretty amazingly dense technical. I would encourage everyone, if you have questions, stuff, just email us, call us. We're happy to answer. I'm sure I will continue to learn more little tips and tricks. You may notice there were things that I didn't cover on the RBE3s. One of them was UM. That little UM field here, that's a quite nasty little advanced field and independent, but boy, it's just, it was too much material. I feel like even then I rushed through some of the stuff, on the force calculation and stuff, but it's dense. Hopefully you guys have enough material to feel comfortable and you can learn at your own pace, which is really the best learning. I am going to turn this seminar off. You guys can find the notes and everything. I'll have it posted early next week. It's a big file. Guys, have a good rest of the day, and we'll talk later. Bye-bye.